Hey gang, and welcome back to another worksheet solutions walkthrough for the worksheet, practicing reactions of carboxylic acid derivatives. Okay gang, if you're watching this video, then you probably know the drill about worksheet solutions walkthroughs, but if this is your first one, well, welcome, by the way. Here's how they usually go. You have tried a worksheet on jOeCHEM, you looked at the answers, but maybe you still have a little bit of confusion, and that's totally fine, because you're in the right place. In this video, we're going to go over this worksheet. I'm going to show you step by step how I arrived at each of the answers you've already seen or maybe haven't already seen on the solutions key. And, yeah, we'll have a time, and hopefully by the end, zero confusion about carboxylic acid derivatives. There are a lot of new functional groups that we just got introduced to. There's little variations between, some of them, but it all comes back to the addition elimination mechanism. So let's get after it. Okay gang, because there are so many problems on this worksheet, what I want to do is I'm going to probably do each section in one or two clips. So here I'll do the first of two clips. You can see that up there. You'll see the topic on the top right corner of the board, and I'm going to have the answers shown here. And what we're going to do is I'm just going to kind of show you mechanistically very quickly, how each answer was arrived at. So this video isn't a bajillion minutes long. Okay. So if we look at this first problem right here, if we take a look at what we see multiple steps, we see this is our starting material. Obviously, you wouldn't know that's the product, but we have it shown. So take it one step at a time like you usually would. In this first step, we see we have a primary alcohol, and you can see we have Jones oxidation reagents. We have sodium dichromate and H2SO4. We know that oxidizes our alcohol, as much as it possibly can get oxidized. So that gives us a carboxylic acid right off the bat. So then for step 2, remember, SOCl2, PBr3, those are those great reagents that we can use to take a halogen, whichever one you're dealing with here, it's chlorine, and do SN2 in a great, unique way so that OH can be a good leaving group. So what you get here is, I'll even do as a step 2, 1 and 2, that SLCl2 right here replaces your OH with the Cl. And now you can see why this fits in the acid halide section. Step number 3. What you should see right here is a nucleophile, right? You have this right here. So you have an O-, you have a negative oxygen, and this is going to do an addition elimination mechanism, but just the one time, right? This falls in the category of a soft nucleophile because remember, this negative charge, one of the things that makes a soft nucleophile is if you have a negative charge, but it's delocalized via resonance, okay? So this negative charge isn't so, concentrated and localized right here on that atom. It's spread out from, amongst a couple atoms. So what you would get is, let's do this right here. I can show you the attack at first. You would get the attack right here. Electrons kick up, so you attack on the carbonyl carbon. So the way that goes is we'd have the O- over here. We'd have this new carboxylate added right here. We have chlorine right here, and no surprise, we have a good leaving group in Cl-. So we did the addition, and now we need to, we created our tetrahedral intermediate. Now we collapse the tetrahedral intermediate, we kick chlorine off, and that's why you get this product right here, because right off of your carbonyl carbon, you have an oxygen. And I forgot, this needs to be here. So that is my mistake. This should have been there from the get-go. So you actually create an acid anhydride. So I apologize, that was wrong at first. So it is now fixed, right? You see you have carbonyl, oxygen, carbonyl, and that's exactly what we have in our product over there. Okay, that's the first one. So moving right along to this problem right here. Again, what you see is the first step is going to be the replacement of this OH with a bromine, right? Because the PBr3 goes through an SN2 mechanism, replaces the OH. So what you get right here is an acid bromide, which now makes sense that why it's in the acid halide section. And then we have excess methyl grignard, okay? And remember, this is a hard nucleophile. This will do addition 2 times. So you'll have an attack here. This will kick up. We will kick back down and kick bromine off. So as kind of 2A, if you will, you would get an addition of a CH3, but you get a ketone, okay? Right, but we have excess Grignard, so we will attack again, because we know we can attack ketones with Grignards. This time, no addition elimination, just the addition. So to finish out 2, we have an O minus, and then we just have the 2 CH3s. So you can see the 2 CH3s in our product over there. We have the O minus right here, and it's at the end that you see we have this workup with deuterium, right? It's not hydronium, it's not H3O+, it's D3O+. So that's why the O minus right here grabs D+, and that's why you get OD over there in your final answer, okay? So, last but not least, and at least for this first part, right, we have this acid chloride straight up, and you see we have a cuprate. Now remember, when you're looking at a cuprate, you're just concerned with what's inside the parentheses, right? So this is our nucleophile, and remember, this is a soft nucleophile, right? Our soft nucleophiles add to acid halides once, our hard nucleophiles add twice. So what we just have here is just going to be the addition of 1 time right here. So there's our addition. You can see I'm going to do some extra work over here in the margin. So we have the O minus, we have the Cl, and I just added 1, 2, 3 carbon. So 1, 2, 3. Then we formed our tetrahedral intermediate. Now it's going to collapse, and then we kick chlorine off. So that's why you can see we have off of the ring 1, 2, 3, 4. 1, 2, 3, 4. That's where the reaction stops. Okay, now that's the first part of the 2 parts of acid halides. Let me clean this up. We'll tackle the last 3 plus the follow-up question. Okay, gang, to finish out acid halides, if we take a look right here, we have 3 complete the reaction problems and then kind of this concept justification problem. So if we take a look in this first reaction right here, so what I'm going to do from here on out is I'm going to draw the answers in blue. So if you can see, this is a fill in the reagent question, and if you ignore this, we basically need to figure out how do we go from an acid bromide, acid halide, to this aldehyde. Now what you can see is we've done a reduction, right? We've basically, we have put in a bond to hydrogen on this carbon. So what you might be thinking is we need a source of H minus. And remember, we have all these sources of H minus now, right? We have diol, we have NABH4 and ethanol, we have lithium aluminum hydride. Here we need a source of hydride that is not that reactive because we have a very, 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 very reactive carboxylic acid derivative. The most reactive. So we need a very mild, source of H minus so that we only attack once. We only do one, attack via addition elimination, right? So the best, source that you can use in this case where you only want to attack once with an acid halide is the lithium tritert butoxy aluminum hydride. Such a mouthful. I literally had to look it up before I started filming this section of the video. It's crazy. It's a super long word. So this is your very, 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 very mild source of H minus, right? What this will do is this will just attack the one time. You're going to first add and then kick electrons up. You'll form your tetrahedral intermediate, and then the electrons swing back down, and then you boot off bromine, and you're going to have H2O that's going to just provide some workup. You might, some teachers may have you include this, some may not. I included it just in case. So that is right here your fill in the reagent. So down here, what do we have going on? So you'd see, okay, acid bromide, and you would see, okay, I have an alcohol and pyridine. And there's a reason why there's an asterisk because these will correspond to this question down here. This is again just going to be an addition elimination mechanism. And here again, we just have a soft nucleophile because it's a neutral nucleophile. It's not super negative. It's not rearing to attack twice, just the once. Okay? So if you want to go through it mechanistically, again, what happens is you just attack first the carbonyl carbon, you kick electrons up. So what I can even do, now that I've shown you that, is just show you what the tetrahedral intermediate looks like real quick. O minus, that's the carbonyl. You have the oxygen up here, right? It's, an oxygen with 3 carbons. You see the oxygen with 3 carbons. It actually is a positive charge. That's key. I'm going to leave that up. Then you have the bromine. Tetrahedral intermediate collapses. You form the bond, reform the carbonyl. You boot bromine off, good leaving group. And you get, at first, you get this. And then the pyridine is here. to clean this up. Okay? Pyridine looks like this. You can use whatever base you'd like, but pyridine is a very, it's just gonna, basically if you toss it in, it's just gonna clean up an acid-base reaction, you know, via an acid-base reaction if there's one to, you know, go ahead and do. That's why pyridine is included here. That's why it helps us out. Okay? So I'm gonna erase, oh, I'll leave that for there. Leave that for now. Down here, very similar reaction. We have two equivalents of ethylamine with our, oh, and you can see we made an ester. Right here we have our acid bromide, two equivalents of amine. So when you, and if you're getting better at these, what I like to kind of see is I see, okay, I have an alcohol. I know I'm going to be attacking with this. When I smush that that oxygen onto the carbonyl carbon, because that carbonyl will stay via the addition elimination mechanism, you get the ester. Similar to here, when we cozy up this nitrogen, which is our nucleophilic atom, through addition elimination on this carbonyl carbon, we're going to get an amide. You'll get better at kind of recognizing those patterns when you just start smushing stuff together. But again, right, we attack, electrons kick up. What I'll even do is down here, I'll show you, we have this, we have nitrogen with two hydrogens with a plus charge, and we have the bromine. Electrons kick back down, we boot bromine off. That's the elimination in our addition elimination. So at first, right, we go from here to here, we actually have this, okay? And very similar, why we include the pyridine, this extra equivalent of amine is there just to clean up. Because right here, if we don't clean up, we actually have two good leaving groups, and the very thing that we booted off, the bromine or some other nucleophile, could just attack the carbonyl carbon and do an addition elimination, because this is not that easy, or sorry, this is not that hard to kick off. It's protonated, it's rare and easily able to be ejected. So this extra equivalent of base is to make sure that once you've added the thing you're trying to add, you quickly deprotonate it and make it less of a good leaving group so that something can attack and kick it off. And that's the answer to this question down here. Okay, gang, so let me, just to show you, the extra base helps just clean up what you're actually trying to stick on the carbonyl that you are attacking. Okay, gang, that does it for acid halides. On to the next section. Okay, gang, rolling into the first take of acid anhydrides. So remember, an acid anhydride, they are honestly, to my eye, a very weird looking functional group. So you have carbonyl, remember C double bonded O, oxygen, C double bonded O. So it's, carbonyl, oxygen, carbonyl, okay? So in the first three, you see in this first problem, right? What I'll do is I might refer to these as asymmetric or symmetrical carbonyls, or acid anhydrides. So if we're the same on both sides like we are right here, this is a symmetrical acid anhydride. And if we are different, it's an asymmetrical acid anhydride. So for this right here, right, we see that we have a cuprate over the arrow. That's all we have. So remember, when you see cuprate, I want you to be thinking soft nucleophile. It attacks, does 1,4 additions. Or in the case of really reactive carboxylic acid derivatives, it does one round of addition elimination mechanism or attack. So when you see this, remember what we really see is Me minus, like that, right? Now, this is asymmetric. So this, methyl anion has a choice. Does it attack this carbonyl or does it attack this carbonyl? And if you're thinking, it can't be sterics, it is sterics, right? This is meant to just be a little refresher on some of one of your early concepts that you learned in organic chemistry, is that if this methyl anion has the choice to attack this carbonyl or this carbonyl, it's going to go where it's easiest. It's going to go where the sterics are the nicest, right? The kindest. And that happens to be on this carbonyl right here. So we're going to attack. And then remember, electrons kick up. And if I have enough space to do this, that initially looks like this. O minus, methyl, and then just the two carbons right here. And then remember, right, that's the addition. Let's do the elimination. We have a tetrahedral intermediate. Let's collapse it. And this is maybe what I think is hardest about acid anhydrides for people, is that when you collapse this, someone thinks like, that's not a good leaving group, but it is, because when this breaks, this charge you get right here is resonance stabilized. So you're splitting this bond right here. So you get a ketone over here, which is, you see 1, 2 carbons and then carbonyl. 1, 2 carbonyl. And that carbonyl is attached to the methyl group, so that's why we got that ketone product. And you get this right here, so that oxygen will have a minus sign. And then this is a great, acid anhydrides are reactive because the leaving group you produce, that charge that has to, is created is resonance stabilized. So great leaving group, as even though it looks big and bulky, that's fine. Don't worry about that. The resonance is what makes it such a good leaving group. And remember, we're only doing the attack here because cuprate's less reactive in terms of the family of organometallics that we are aware of. Okay, so now down here. So you're seeing the answer in blue. So what this would really look like is you have an acid anhydride, and then you see over here, you can just assume that there's a 2 here because we are symmetrical. We're just reducing this down as much as we can, right? You can see neither of these carbonyls have bonds to hydrogen. Over here, there are 2 bonds to hydrogen on that carbon that was once our carbonyl carbon. Because you can see in the structure, there's only one section that has 2 carbons. So these 2 carbons must represent either these 2 carbons or these 2 carbons, right? So there's nothing here in terms of, a double bond that would be acid sensitive, because remember when we use LAH, we do use acid, so we need to be aware of that. So to just kind of reduce this to smithereens, just grab your aggressive friend, lithium aluminum hydride, toss it in there, have a time, let it reduce it all the way down. And then last but not least, for this first take at acid anhydrides, you can see right here, obviously ignore the blue, we have a symmetrical acid anhydride, and then we have ethanol. So again, a soft nucleophile, it's neutral, but the nucleophilic atom here is oxygen. This oxygen won't care which carbonyl to attack, but it's going to attack one of them. So we're going to do an addition, and then we will kick electrons up. So if you want to think about it, we'd have O minus, we'd have O, ET, H, and a plus. We have the oxygen, we have the carbonyl, and then this. Then we have a tetrahedral intermediate. We've added, now let's collapse it and eliminate. So you can do this. So at first you will have this. And if you had on your answer that, this grabbed this, and you kind of had this situation, that's totally fine too. Something is going to pick up the additional hydrogen on this oxygen and eliminate that positive charge. In fact, what it could have also been, maybe you have this minus charge right here, you have H plus, another ethanol could have came along and done it. It doesn't really matter, as long as you have the ester product and you represent this and you have the carbons accounted for. In my book, that's a correct answer. Okay, that's part 1. Let's finish out with part 2. To finish out acid anhydrides, we have these 3, complete the reaction type questions. So in this first problem right here, so if this looks different, it's because even though you've seen this already, it's a different, visual representation of a reagent we've seen. So this right here, of course, we have this cyclic anhydride, acid anhydride, but let's look at this. This is lithium tritert butoxy aluminum hydride, right? This is the same reagent as, let me see if I can remember how to write this. It's an adventure every single time. Oh, no. I think it's, it doesn't matter really, but I just want to show you, I just wanted to give you a different look. I just wanted to highlight that these are in fact the same, and you might see them in, either form. So when you see this, it's absurdly long, but remember, it's a mild source of hydride, of H minus. So what I liked about this problem is that, it doesn't matter which carbonyl we're going to attack in the acid anhydride because we are symmetrical, but you can see that we're going to be breaking our ring. So in this attack, right, you can see I'm going to attack right here and electrons will kick up. So I'll do some work right here. So you can see what we will have is we will have O minus, we have a new hydrogen, and we have an oxygen, and we didn't touch this carbonyl at all. We formed a tetrahedral intermediate in the addition, and now we're going to collapse it and do the elimination, right? Electrons come down, and then this is my leaving group. This part of the ring, this bond is going to break, okay? So at this point, what will help is if we number. And I'm going to number 1, 2, 3, 4, and 5. I'm just numbering the carbons. Yeah, I could give this oxygen a 6 if I wanted to. You can go ahead and do that. But you're going to see on carbon 1, I'm going to have an aldehyde, and I'm going to have a 5-carbon chain. So if you look over here, this is carbon 1, It's an aldehyde. It has a hydrogen. This is carbon 2. This is 3, 4, 5. And then if I want to label the oxygen 6, I can do that. And you can see we're going to have an O minus, and the water will help quench that negative charge. Okay? Right? At first it will look like this. But this can grab H from water. Okay? So now in this second problem right here, so this would be not given to us, we would see, okay, we have Grignard, we have H plus, and really what I'll make sure to specify here is that this was excess. So you can see we have a Grignard product, right? We obviously see we have an alcohol, and I think what you can make out is we do have, so this is isobutyl Grignard, right? Common name and coming back, right? Because we've 1, 2, 3, 4 carbons, and we're attached on that N carbon, and I think you can see 2 isobutyl groups attached to that carbon right there. So it's no surprise that this was once a carbonyl, and of course this is in the acid anhydride section, right? We could have accomplished this with, for example, an acid halide, but to make this work with an acid anhydride, because we only see one product to, we might be thinking symmetrical acid anhydride. We only want to produce one type of Grignard product. So you're at least going to have a benzene ring with a carbon in the benzylic position that was a carbonyl. So what you just need is 2 of them, and you just smush them together. So this is, it doesn't matter which carbon gets attacked, but the same one is going to get attacked twice, right? And that's why we have the excess Grignard reagent. So that, if it's this carbon right here, this ends up being the leaving group. After the first attack, you're going to have something like this, right? Because that's 1, 2, 3, 4. And then the second isobutyl Grignard attacks right there. That's how you get 2 of them, okay? And then last but not least for this section, we're just going to hydrolyze an acid anhydride, right? Hydrolyze meaning we're going to use water to break it up. Again, water is, so this was a hard nucleophile attacking twice. Again, we're back to a soft nucleophile attacking once, just like we saw up here. Water, again, if you're sick of the addition elimination mechanism, that's good. That means you're seeing the pattern. It's happening over and over and over again. The hardest question you usually need to answer is it happening once or is it happening twice? So if we had, I'll do the O minus over here. I'll do the OHH plus over here. We have the oxygen. And then we have, again, 1, 2, 3, carbonyl. 1, 2, 3. Yeah, I got that right. So then that's the addition. Then we collapse the tetrahedral intermediate. Kick off our leaving group, we do the elimination. And at first, right, we have a positive charge there. At first, we would have something along the lines of, let's see, something like this. As well as this 3-carbon carboxylate. And again, something will clean this up. You'll get the carboxylic acid. Maybe this is what cleans it up, and then this doesn't have a negative charge. In fact, it has a positive charge. But you also have water here. Maybe water deprotonates right there. You have a whole bunch of options. As long as you break this up and you have this carboxylic acid and something that resembles that as well, you're good to go. Okay, gang, that was it for acid anhydrides. Next, we tackle esters. So let's go. Okay, gang, so you probably saw the ester section and we're like, what the heck is going on? There are more problems here. There's maybe just a little bit more that you can do with esters, or at least that's what I thought. So there's actually going to be 3 takes for this section, so we're just going to go right on through. Okay? So in this first section, we see we have a cyclic ester, which you can actually call a lactone, just for a, I want to call it a fun fact, but is it really that fun? So what we can do here is with diisobutyl aluminum hydride, okay? This is a source of H-. It is more aggressive than your lithium tritert butoxy aluminum hydride. It's more aggressive than that, but it's still in that realm of soft nucleophiles. It's going to attack once, particularly what you will probably most likely use it for is, and I realized this should be a hydrogen, I'm sorry. Here's down to aldehydes. Sorry, yeah, that OH was extra. So it's great for ester to aldehyde, attacking once in a soft nucleophile fashion, just that one addition elimination mechanism. So what we can do here is similar to that acid anhydride, cyclic acid anhydride problem, is we will attack right here, the electrons kick up, then they kick back down, and then we boot off this, what will be an O minus at first. So at first, we get this. We do get an O minus. It's not the best leaving group in the world, but that's why we have the, workup present. This will find water, it will grab H plus from water, and you'll go from having that O minus, right, to having the OH. So diisobutyl aluminum hydride, great for that ester to aldehyde 1 attack reduction, okay? So now from here, we actually have an interesting problem that you will dive more into when you start talking about ester enolates. So this right here, we see an enolate, we see an ester. When you see enolates, again, remember, with soft nucleophiles, if you have a charge that's distributed, shared amongst the atoms, it's not located in one position. It's not that negative, like very concentrated negativity. This is a soft nucleophile, okay? And we've used enolates as nucleophiles before, but here we're going to attack an ester. So what's going to happen is electrons swing down, and remember, we are bonding from the carbon that's a part of the double bond that's not the carbonyl carbon, aka the alpha carbon. The alpha carbon then reaches out, attacks the carbonyl carbon, then we kick electrons up. So at this point, right, we have this is just a phenyl group, we have O minus, we have this giant ester right here. Let me see if I can squeeze this in nicely. So you can see this is the alpha carbon, that's this carbon right here. This is this carbon, and then you have the 2 extra, and then we have the OET. Then your tetrahedral intermediate collapse, and you boot that off. Now you might be thinking, well, Joe, this is not a good leaving group. And you are correct, right? That's not a good leaving group. And the reason why this works is because there is a hydrogen available at this position right here. You'll dig into this more when you talk about clays and condensations. Whoops. Well, the whole point is that this does work out. That's not a good leaving group, but there's a very quick acid-base reaction that happens right after the fact, which makes everything okay. You'll talk more about that with clays and condensations, but I did want to kind of sneak this in early before you got there. So you just do the 1 attack, right? You bond from the alpha carbon to the carbonyl carbon, you boot off the OET, and that's okay, trust me, okay? So now down here, what I'm going to do is erase this a little bit. Down here, first step, we're just going to deprotonate the carboxylic acid. So as a first step, you're going to have O minus, and then you're going to have this benzene ring, O minus. Then as a second step, that negative oxygen is going to do SN2 on a methyl bromide. So as a second step, we now have, I'll just do methyl O this, and now you can see that was just a sneaky way of generating an ester, right? We have an ester now. Third step, ETOH and H2SO4. Normally, if we just had a carboxylic acid, this would be Fischer esterification. And it kind of is, but this is just trans esterification. So we're going to be swapping out this kind of like alcohol portion of our ester, right, or the ether portion of our ester, whatever you want to call it, with, it's not going to be OME, it's going to be OET, because the H2SO4 protonates the carbonyl oxygen. That makes it easy enough for your alcohol that you're tossing in to attack, and then you go through your classic addition elimination mechanism. But since we're in acidic presence, you can grab H plus whenever you need to make something a better leaving group. You can deprotonate something when you want it to stay, and that results in the swapping out of the O-methyl with the O-ethyl, and then producing this, O-methyl as methanol. Okay? Transesterification. Now down here, so this was transesterification. Down here we have saponification, okay? So this is the process, saponification. This is the process that soap is made in an industrial setting. So we do have a basic environment, right? You see NaOH and you see heat. That's gonna help us overcome the fact that we're gonna be kicking off a leaving group that's not amazing. So what's gonna happen first is you have hydroxide come in. That is our nucleophile. It's going to attack the carbonyl carbon. You just kick electrons up. Here comes the addition. So then you have O minus. You have the newly added OH. you have this section right here. Did I lose any carbons? No, I guess I could choose to draw this like this. Then you swing these down, you boot this off. That's how you make your 1, 2, 3 carboxylic acid right over here. And at first, right, what happens right away is the alkoxide you produce just quickly grabs the hydrogen right there. So at first, you have to, compensate for the fact that you did kick off a bad leaving group. You had enough heat to do it at first, but then we have the second step of hydronium. Everyone gets protonated, everyone gets happy, but it's the heat that allows this to happen, and your hydroxide does an addition elimination mechanism, just like we've done time and time again. So now down here, you see we have our good friend lithium aluminum hydride in excess. So we have this ester right here. So basically, we are going to reduce as much as we possibly can. So what's going to happen is we have H-, a very aggressive form of H-, a hard nucleophile. We're going to attack, electrons kick up, then they're going to swing back down, and then we boot this off onto there. So as a first kind of attack step, we go from having O- to having this aldehyde right here, but we're not done. We have another H- that comes in and just does a regular attack on the carbonyl carbon in the aldehyde. So after this first step right here, what I want you to be thinking is you've taken that ester, you broke the ring, so you have an O-, and then you also have another O-, right? Really, you have the 2 carbons here, the 2 carbons here, and the OH, and you've just broken that bond, and everything is as reduced as it possibly can be. Now you have the D3O+, and all that does is just, we have D+ floating around, and each of these protonate up to be OD. If this was H3O+, they'd both be OHs. Okay, gang, that does it for the first take. Let's move on to part 2. So gang, at the time of recording, I actually realized I duplicated a page in the solutions, so I thought there were more ester problems, but they were just the same page twice. So this is actually just the last take for the ester section. We have 2 problems, and then I'm kind of going to explain more about this because there's a follow-up question about why we only see 50% product here, and we'll dig into that. So this first problem up here, this is just an ester being attacked by, here it's ammonium, but it's an amine to go from an ester to an amide, right? So what's happening here is we would, the same old story. We have a soft nucleophile. It's going to attack the carbonyl carbon. You kick these up. You generate your tetrahedral intermediate. Whoa. So we have O-. We have the NH3 plus now because nitrogen is sharing a lone pair that it once had for itself. It goes from neutral to positive. And then we have the OPH, tetrahedral intermediate. Well, actually, and you can even do this, if you want to. Some people, this can kind of be like an acid-base step if you'd like it to be. You can just kind of have this. It's kind of like an intramolecular acid-base. Or you can collapse and then do the acid-base reaction after the fact. It's really up to you. I've seen a lot of people do that. So you can have the O-, you can have the OPH plus here. The NH2, this collapses, you boot that off, you get your amide, and then you get the corresponding alcohol, whatever kind of piece you have over there, part of your ester, okay? Now, let's finish off esters with this problem and the explanation as to why we get 50% product here and 50% of our starting material just untouched. Okay, so I'll kind of explain the problem, which will show mechanistically how we get our answer right here. So obviously we have just one equivalent of methyl grignard for our ester. One equivalent, right? There's an implied 1 here. There's an implied 1 here. So the very first thing that will happen is we have our CH3-. It's going to attack the carbonyl carbon. Electrons kick up. We generate our tetrahedral intermediate, the beginning of our addition elimination mechanism. So at this point, we have O-, we just added a CH3, and we have our OET. At this point, we collapse our tetrahedral intermediate, electrons kick off, we boot off the OF, the ethoxide, and here's where we see the cause of what we observe. We generate a carbonyl, and here it happens to be a ketone. Now, we've done this in the past, right, with acid halides, acid anhydrides, but here's the kicker. We talked about carboxylic acid derivative reactivity. yes, acid halides and yes, acid anhydrides are much more reactive than ketones. However, esters are so much less reactive than the carbonyl you generate here. So after the first attack that occurs here produces this carbonyl, the next Grignard has to make a choice. Do I go for the new thing that just got generated that I'm more attracted to in terms of reactivity? Or do I go back to the blend or ester? And the answer is, as soon as you start generating ketone, your methyl or your hard nucleophile, whatever you're working with, starts attacking that new thing. So you start consuming so every one ester starts consuming 2 of your hard nucleophiles. So you kind of have a 1-to-2 ratio. So the next thing that happens is another methyl Grignard attacks right there. Electrons kick up. You produce O minus, CH3, CH3, and then, protonation happens. So we could just even protonate across this arrow to make it simpler. But the idea is, the reason why is if you have an equal amount of esters, you do hard nucleophile, right? A lot of the times you have excess here and then you don't worry about it. But a good test question I've seen is explain why if you have one equivalent of ester and one equivalent of hard nucleophile, a nucleophile that's going to attack a carbonyl 2 times via additional elimination, why do you see 50% product and 50% of your original carbonyl just standing in the corner twiddling its thumbs? The reason is by the nature of attacking that initial carbonyl, you generate a carbonyl that you want to react with even more than the initial starting material. That does not happen when you have an acid bromide, right? If you attack an acid bromide or anhydride, whatever, and you do this flow, you create a ketone. Ketones are not as reactive as acid bromide. So your hard nucleophile keeps attacking the most reactive thing until it's gone. However, the situation's flipped here. You attack something that's less reactive and you actually generate something more reactive. So that's why you see this weird disparity with esters. Okay, gang? It's been a heck of a video. We just have amides. Stick with me and we'll finish this walkthrough. To finish out this video, gang, we just have the one take for amides. Okay, so if we take a look right here, we just have 4 problems, and then we need to also explain why pyridine is necessary, and if we know the name for a cyclic amide, then we get bonus points. Okay, so if we take a look right here, right up here, this is just a simple amide to ester transformation. So because remember, kicking off nitrogen and putting a negative charge on it, that is super unfavorable. We know that nitrogen with negative charges makes super strong bases. Strong base means unstable base. Remember our good leaving groups, we can get away with kicking off an O-, but we have to put in some heat or we have to have a nice acid-base reaction at the end, that light at the end of the tunnel. That's not the case with nitrogen. So this works if we have H2SO4 in the mix because we can have an abundance of protons to help us quench negative charge when necessary. I'm not going to show this. You know the drill by now. We'd protonate the carbonyl oxygen. We'd have our oxygen in ethanol, attack, electrons boot up. We protonate this. They come back down. You kick this off. You get the deal. Okay? Now, remember, in this second problem right here with lithium aluminum hydride, right? Remember that amides, we've talked about this, are the least reactive carboxylic acid derivative, right? Because of the fact that nitrogen donates so much electron density towards the carbonyl carbon. As a result, you only have one option to reduce them, and it's with our very aggressive friend, lithium aluminum hydride, and it's different than all the other reductions we've done before. It's super strange in that you just kind of erase the carbonyl carbon, or the carbonyl oxygen. You just kind of erase this, and that's your reduction. Very good, classic complete the reaction problem I've seen, okay? Now down here, we are just doing amide hydrolysis, okay? So again, it's the same problem as up here, except instead of ethanol, water is our nucleophile and hydronium is the acid. So again, you're gonna protonate the carbonyl oxygen, water attacks the carbonyl carbon, protonate where necessary, make this a good enough leaving group, and then swing the electrons back down and you boot off nitrogen, okay? Now I like this problem down here. I think this might be the best of the bunch. Okay, so in this problem right here, what I'm going to do is make some space. So in this problem right here, as a first step, we're going to replace the OH with a chlorine via SOCl2. Okay, so as a first step, we have nitrogen. I have 1, 2, 3, 4. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So we have this acid chloride. Now remember, we can definitely make amides with an amine and an acid chloride, an acid halide. That's really what this first step did, was make this carboxylic acid more reactive. So what we have from there is this nitrogen we're going to cyclize. This nitrogen is going to come around and attack, and then these electrons will boot up, and that makes sense in that we can definitely support ring formation, because remember, we like 5 and 6 membered rings. So we're about to form a 5-membered ring with nitrogen in the ring. Step 2. So what I'm going to do here is I'm going to have nitrogen in this. I know I'm going to have a pentagon. This will be 1, 2, 3, 4, and 5. We'll have 2 hydrogens right here. Nitrogen will have a positive charge because we're sharing the lone pair. It's a part of a bond now. We'll fix that in a second. But on carbon 5, we do have that O-, and we do have that Cl. Remember, this is a tetrahedral intermediate. Don't forget that. Tetrahedral intermediate collapses. We kick off that amazing leaving group we have in chlorine. So we're almost done, and this helps answer a follow-up question. Remember with our amide formation before, we just had 2 of our amine. Well, this structure has our amine inside of it. So I mean, yeah, we can have 2 of these, but if we didn't want to, maybe this starting material is expensive. I'm talking like real life, which maybe you don't care about so much. Maybe this is so super expensive. So the, amine we can throw in to help save us is pyridine, right? Pyridine can help take this, deprotonate this, give nitrogen a lone pair back. That's how we get our product. So that's why pyridine here is here. It's for the acid-base cleanup. Acid-base cleanup. And if for bonus points, a cyclic ester is a lactone. A cyclic amide is a lactam. Gang, this was a bear of a walkthrough. So if you're still watching for some odd reason, thanks for getting to this point. But also, if you're watching at all, thank you for financially supporting jOeCHEM. You don't have to, at all. But I appreciate that you did, and I hope you're getting your money's worth. I hope whether you've paid or not paid and you're watching this video, or you're using jOeCHEM at all, I hope it's the tool you're hoping to find. I hope it's helping you make sense of carbon. I hope it's making you a more productive organic chemistry student, and I hope it's helping you achieve your goals, whatever they might be. I hope, I'm so glad you're using jOeCHEM right now. I hope you're using it to the end of your carbon career, and no matter what, I hope to see you all in the next video.